Let's take a look at a couple of concrete examples where we have to use this precise definition of limits. So here in example 1, we've got a graph that shows f of x with limit as x approaches negative 2 of f of x equals negative 1. So here I'm telling you what the limit is. For epsilon equals 2, find the corresponding value of delta greater than 0 that satisfies the condition absolute value of f of x plus 1 is less than epsilon whenever 0 is less than absolute value of x plus 2 is less than delta. How I would start this problem is I want to figure out what x value are we approaching, what is our c if we look back at our definition. So here we're approaching negative 2, so I say c is equal to negative 2. And what is my limit here? My limit in this case, L, is equal to negative 1. So that means, okay, for an x value of 2, that corresponds to a limit of negative 1. This is my L over here. You might look at this last part of the definition over here. You might say, hey, this looks a little bit different, right? We've got f of x plus 1 instead of f of x minus L. But the only reason this is happening is because we have absolute value of f of x minus negative 1, which is why that looks like a plus 1. Same thing over here with x plus 2. What I really have there is x minus negative 2. So that's why that looks a little bit different. It's still the same exact definition here. So I know what x value I'm approaching. I know what my limit is. Let's look at our epsilon in this case. And here our epsilon is equal to 2. So from this limit L, from negative 1, I'm going to move up 2. So I'm going to say this is L plus epsilon here. And I'm going to move down to L minus epsilon down here. I moved 2 down, so I subtracted 2, and then I added 2 to that limit L. And what I'm going to do then is I'm going to take these and I'm going to map them back to the x-axis. I'm going to see, well, what x values correspond to these y values. So if I look right here, L plus epsilon, this corresponds to x equals negative 1. If I take L minus epsilon, take that back over here, that's going to correspond to negative 3 right here. And what I'd like to do is I'd like to figure out, okay, how far are each of these numbers from my c, from the x value that we're approaching? Well, here in this case, my distance between negative 3 and negative 2, this is simply just 1. And then the distance between negative 2 and negative 1, this distance is also 1. This is probably the easiest scenario that we'll have here because the distance on either side of these two numbers is exactly the same, which means that we shouldn't have any issues. Delta in this case will be equal to 1. And if you want to, we can actually go and check this now. So let's take some number that's within 1 unit of negative 2. So let me change my color here. It's a little bit easier to see. As long as I take something that's within 1 unit of negative 2, this means I should end up somewhere between L minus epsilon and L plus epsilon. So if I took, let's say right here, if I took this number, plugged it into my function, I should end up between L minus epsilon and L plus epsilon, and it looks like, yes, I do. I could take any number I wanted. I could take a number even right here that's very, very close to negative 1, but it still puts me between L minus epsilon and L plus epsilon. So in every one of these, you can sort of visually check your answers here by just taking an x value that's within 1 unit of what x value you're approaching, and we should end up with, between L minus epsilon and L plus epsilon. So for this problem, our delta is equal to 1. That is our answer. In example 2 down here, it's a little bit trickier. It says the graph shows g of x with the limit as x approaches 2 of g of x is equal to 3. For each value of epsilon, find the corresponding value of delta greater than 0 that satisfies the condition absolute value of g of x minus 3 is less than epsilon whenever 0 is less than absolute value x minus 2 is less than delta. So let's look at this guy here. So they tell us, okay, the x value that we're approaching here, we're approaching positive 2 this time. So c is equal to a positive 2 this time. And my limit here, in this case, my limit is equal to 3. So the x value that I'm approaching is 2. And the limit in this case is 3. And you might look at this and say, well, hold on a second. We have a hole in our graph right there. Remember that when we have an open circle in our graph, that really means that the graph actually doesn't exist there. For now, I'm going to tell you not to worry about this. We'll talk a little bit more about this in sections 2.2. So keep that in the back of your mind. We will revisit this idea. Right now, I'm just asking you to trust me here. So, all right, we've got our c, we've got our limit L. Let's look at our epsilon here. So this time we said that epsilon is equal to 1. So this is my L. I'm going to take L plus epsilon up here, which would take me to 4. And L minus epsilon down here, that would take me to 2. So I'm just doing 3 plus 1, 3 minus 1. And I'm going to map these both back to my function and see where they land on the x-axis then. So there is L plus epsilon, it maps to 4, so here's c, here's maybe another boundary, and then I have L minus epsilon. If I take that, map it to my function, so I've got 4 right here, and then I've really got this guy right here, which is, oops, not 2.5, excuse me, 1.5 here. So 1.5 there. So the distance between 1.5 and 2, my c here, my distance is 0.5 or 1/2, and over here the distance between 2 and 4 is 2. So this one's a little bit different from the last problem. The distance on either side of c is not quite the same, and that's because we have kind of the slope is changing at that point. So what we can do is we can actually just sort of guess and check, and then I'll tell you the shortcut after this. Let's suppose we want to choose the largest possible delta, right? So we want to choose the biggest possible value of delta that we possibly can here. So I would expect in this case that we would think, okay, let's try delta equals 2. I'm going to try delta equals 2, and I'm going to put a little question mark after that because I don't really know. So what that means is if I take a number between c plus 2 and c minus 2, plug it into my function, I want to end up between L minus epsilon and L plus epsilon. So if you pick a number on the right-hand side of 2, that's within 2 units, right? So if I took, let's just say 3.5 right here, plugged that into my function, that's not going to be a problem. That lands us between L minus epsilon and L plus epsilon. That lands us at about 3.5. But it needs to be true on both sides of 2. So I need to be able to take that number and plug that in on the left-hand side of c equals 2 as well. And if you'll notice here, so let's take a number that's maybe just 1 unit away, not even 2 units away, let's just take 1 unit away. If I took this number right here, if I took 1 and plugged that into my function, right, if I take 1, plug that into my function, it maps it to a y value of 1. That does not land between L minus epsilon and L plus epsilon. That's what I wanted over here. So if you look at this, you say, okay, delta equals 2. If I pick a number on the left-hand side, it doesn't land me in between those two values. Then I know that that value of delta is too big. It's actually too large. We cannot choose that value of delta. So if it's not 2, then it's probably 1/2. Let's try that. Delta equals 1/2. And let's erase just so that we have a little bit more room over here. So this time I'm going to try delta equals 1/2. So I'm going to move 1/2 on the left-hand side, and I'm going to move 1/2 on the right-hand side. So if I take a number that's within 1/2 unit on the left-hand side of 2, plug that into my function, I just want to verify, hey, do I land in between L minus epsilon and L plus epsilon? In this case, yes, I do. It looks like I land right there at 2.5. Now, on the right-hand side, it might seem silly, but I'm going to take a number that's within 1/2 unit of 2, so I might pick, say, 2.25, maybe right here, and I plug that into my function. And this is also certainly going to land me between L minus epsilon and L plus epsilon here. Now, you may end up, if you look at this, you may end up with all this extra space right here, right? You may say, well, I've got all this extra wasted space, but it doesn't work for us on the left-hand side. We said that delta was too big. So in this case, we have to go ahead and say delta equals 1/2. In this case, this is the largest value of delta that makes the statement true for this particular epsilon. Now, if I changed my epsilon, that would also change the value of delta. So if I said, okay, maybe I want to redo this problem, but now I want epsilon to be 2, then my value of delta very well may change based on that change in epsilon.